Well, good morning, everybody. It's an absolute pleasure, and thank you very much to the Obendorf family, and to Ron Levy, and also Kathy Adams, and Hal Dorr for inviting me down here. And it's really a wonderful pleasure to be able to talk with all of you. I walked through the exhibits yesterday, and it's just amazing to see how far we've come from when I went to medical school 20-odd years ago to what you all are developing. It's really amazing. So with that, I'd like to start our slideshow if I can. And one of these is mine. We'll find it. There we go. And down here. So as a personal disclaimer, I'm not an astronaut. I am a flight surgeon, but I get to take care of them. Also, these are my personal views and not those of NASA or the Aerospace Medicine Association, nor of the Air Force or UTMB, but I'm associated with all of those. My main themes I'd like to talk with you this morning are that space does remain important. I'd like to go over some of the historical simulation interested items that we have. I'll also talk to you what a flight surgeon does and talk about our simulation and training. And if we can get to it, I'd like to talk about analog environments. And I have one other disclaimer is that NASA did not invent Velcro, nor did they invent Tang, of course. But we'll take credit for that if you'd like to give it to us. I got interested in space when I was 4.5 years old, when my mother woke me up and she showed me the Apollo moon landing, so I'm dating myself. But I thought it was pretty fantastic, and I could not pull myself away from the television for the next several missions after that. And the other thing that pointed in my, as a child I saw was when the United States and when Russia got together, this was the height of détente, of course, height of the Cold War, and we found some détente. And you know, the Russians and the United States meeting together in outer space was something really special to me. Actually, you can see here the crew, General Tom Stafford. I actually just talked with him this morning. These guys are still alive. Leonov is the first human to walk in space, and it's really amazing to be able to continue to take care of them. Contrary to the public belief, with the closing of the Space Shuttle program, we're still open for business. We do have the International Space Station open as a test bed for future exploration. NASA's trying to foster a commercial industry to be able to get to low Earth orbit, and we're really trying to design an architecture to send humans back to the moon and on to Mars. This is an international effort here. The International Space Station, which you can see with your own eye several evenings a month, is 1 million pounds in orbit over 2 football fields in surface area. Just an incredible accomplishment, I think. A lot of these pieces and parts never got together until they got together in space. They put them together in simulations. They put them together in different assembly locations around the world, and they were successful. It is very much an international effort. We have 5 major partners: Canada, Japan, the United States, Russia, and Europe, and countless other countries that are working together to bring this to fruition. NASA's, I think, still important, too, when it comes to looking at environmental observations of the Earth, both when it comes to weather and changes in the climate. Also, I think that space is the ultimate in environmental protection. Flying here from Houston yesterday, I was looking down in Arizona, and you could look down and you could see some potential asteroid craters and things of that nature. And we hope that we'll never have, in our lifetime, a Yucatan meteor dinosaur killer. You can see there on the right-hand side. But NASA and there are several folks that are looking to make sure this doesn't happen again, or if we do find them, we know how to respond to them. I also think this is the ultimate environmental protection, in that there's lots of resources there in space, but we need to keep an eye out. For those who are monitoring space weather, you can also monitor asteroid weather. This is a list of asteroids that just this week came near the Earth. They also found a 15-meter meteor that came between here and the moon. Actually, it was 0.2 lunar distances away, so it's a close miss. There's also a lot of stuff that's in orbit now when it comes to satellites, and we're all extremely dependent on satellites. Sometimes they do hit, and this is the outline of what the Chinese satellite when it hit one of the Iridium satellites, and now the debris that's in orbit. This is very important, in that it's in the same orbit as the International Space Station. Only about 6% of the material has fallen to Earth now, and the rest of it's got to come down sometime, so we're constantly having a look at that. things do fall down, and this is in Kazakhstan, and it's interesting, the Russians and the Kazakhs look at things a little bit different. There was a story in the Russian press a few years ago where a Russian or a Kazakhstan farmer heard a big bang behind his house, and he went out and looked, and a piece of rocket material hit his outhouse, and he was not as worried about what had happened to his house, but he was more worried about who was going to pay to repair that outhouse. So, but things do come down, and you know, they're going to continue to come down. So what's important about simulations, and you all are doing the lion's share of the new innovations, of course, but you know, the top of the line is communication. How do we talk with each other? You know, at NASA, the medical portions are about this compared to the medical personnel, about this compared to the number of engineers and crew and things like that. So we have to learn how to talk with each other and explain what's important when we're running through our simulations. We have to have clear goals. You have to decide what the mission success is, what the objectives, but we also have to maintain patient safety and crew safety. Procedures are very, very important. You know, we really list, you know, in excruciating detail throughout the mission what's going to happen and how we're going to design that. But we have to be able to change those procedures when we hit reasons to change them. Having a clear line of responsibility, who is in charge, you know, and also who is responsible for what portions of the simulation. And also, I know this is a different group. There's not only physicians here, there's lots of nurses, there's support staff. It's very, very important to recognize each of those persons as professionals and as a member of the team, because any one of those persons has a very important part to bring to the simulation and to the actual delivery of medical care. And if you forget about that, you're going to have some failures. And how do you integrate equipment? How do you integrate different systems? But at NASA, we also have to focus on crisis management. Things happen in space, and they happen very, very rapidly. And also, you can use simulations to develop new or decide on how you're going to have a concept of operations. Way back in the Gemini period, when we had 2 astronauts in one craft, they actually thought about how they were going to return the Gemini spacecraft, and they thought about using a parafoil. They decided they couldn't use that because it was too ungainly how they're going to land, and they actually went back to using parachutes and landing in the water. Same thing with simulations. You need to do them adequately. Gene Cernan told me that he was actually, when he did his spacewalk out of the Gemini capsule, they hadn't really adequately simulated it. And so when he got out of the spacecraft, his suit overheated, his visor fogged over. When he went back to behind the spacecraft in the back where he was trying to get back there, he found he didn't have enough handholds. And when he tried to get back in, actually, he really had to bend his knees and almost deflate his spacesuit to be able to get back in. It was everything he could do to get back in, and that was because they hadn't simulated it adequately. Another main point is to share what you learn when it comes to simulations. You know, as I mentioned, back in the Cold War, we weren't talking to the Russians. And during Apollo 1, where, you know, fortunately, or a lot of people know what happened there is that we had a crew of 3. They were under high-pressure oxygen. There was some rushed wiring done, and they had a fire inside, and all 3 perished. But what we didn't know is that the same sort of tragedy had happened on the Russian side, that a cosmonaut was also under 100% O2 in a chamber, in an isolation chamber. At the end of his mission, he actually tossed a little cotton ball over towards a heater, a space heater, and it ignited and it killed him as well. But we weren't sharing at that time. So the bottom line here is to, when you're learning things about simulation, share them with the other groups so that you can avoid that. When you do have a problem or you do have a crisis happen in a simulation or in a real world event, avoid trying to put you know, who was to blame. Put the pins back in the hand grenade, so to speak, and decide how you're going to take care of the issue. You know, Apollo 13, if you read the report, they actually said on the loops, Gene Kranz said, don't do anything that's going to make anything worse here. You know, you want to step back and see what's going on and then make some decisions. Same thing with if you're flying in an airplane. A lot of times you go into turbulence and, you know, everything's going haywire, your unusual attitudes. A lot of times if you just take your hands off the control, the airplane will actually right itself. So don't do things and going to make things worse. The Apollo 13 is a very good case report. You know, when they were going back to the moon, they had pulled the LEM out of its storage area, and then they put that together with the command module. Then when they shifted the oxygen tank around, the fluid around inside the oxygen tank, it exploded. Had it happened in any other location or any other time, they would have perished. If it happened when they were on the moon, or if they had it happen on the return back, they would have not been able to come back. So sometimes luck does help you. Also, during that event, you go back and read about it, but as you guys may know, they had to come up with a CO2 scrubber to remove the carbon dioxide. It was a new problem, but Why were they successful? Well, because they had established teams. They knew how to communicate. They knew the materials that they had on board, and they had the ability to communicate with each other. They also had clear lines of leadership. And then they fabricated it, and they tested it, they simulated it on the ground, and they were able to then construct it in orbit and allow the astronauts to remove the CO2 and bring home. So it's very important to keep your organization flat, especially when it comes to an interprofessional organization. You know, we all come from several hierarchies of nursing school and medical school, but how do you accept other people that are in your groups, and how do you accept other people that have a big part to play when it comes to simulations? Another event reminds me to tell you about is that, of course, simulations are very important when it comes to the real day, and an individual can save a mission. This is an example here. Apollo 12, when it was launching, it was struck by lightning twice. And when they're in their ascent phase, 8.5 minutes, they actually lost all their avionics and all the panels in front of them. And so the crew was actually flying blind. But there was an individual flight controller who actually had seen this in a simulation during one of the tests. And he said, I've seen it. You just flip this switch to auxiliary. No one on the ground crew other than he had knew what this switch was. No one else could recognize it. Actually, the crew on board the Apollo spacecraft, only one of them knew what this switch was. And so they trusted him. And they said, are you sure you know what's happening? Yes, I've seen it in simulation. So they threw the switch. The avionics came back on, and reportedly Conrad laughed his way all the way to orbit as he realized his life was saved. So bottom line, important is to pay attention to people and pay attention to your simulations. How are you successful in a simulation? Team and trust is what is paramount. Respect each other and also respect the leadership. But you have to have personal leadership to understand your own system and understand your portion of the team, and then trust your leader that they're going to make the right decision. Do things as a team when you're making the decisions, but also recognize that the team leader may have to end up making a decision as well. So what is this flight surgeon? What is a flight-in-flight surgeon? What are the good in simulations when it comes to aerospace medicine? Well, the flight surgeon, and I know there are a couple in the audience here, so I hope I'm saying everything correctly, but basically what a flight surgeon is almost like a family physician or internal medicine. We take care of our flight crews, we take care of their family members, and we all understand what their jobs are. But the interesting thing about a flight surgeon is that we take care of aviators. We sign on the dotted line, so to speak, to let them to continue to fly. And that is an amazing thing if you think about it. If someone were to tell you today or tomorrow and say, well, your health has an issue, you no longer can be a nurse, you no longer can be a physician, that would open your eyes up to the power of that person. And that's what a flight surgeon does. But fortunately, what we do is when we find something that's wrong with one of our patients, we will fix it, we'll get them back on status and get them back flying. That's the trust that we have with them. So, I'm going to skip through a couple of things. One of the neat things you get to do as a flight surgeon is fly. And you know, the astronaut sits in the front seat and the flight surgeon sits in the back seat. And this, I'm going to date myself, but you may be able to see on this, is T-38. It was a jet trainer. This jet trainer was built in 1963, so a little before my time. But it's an absolutely beautiful aircraft. It'll go over Mach. It'll do a 720 in a second and a half or so. And they actually let the flight surgeon fly, which is crazy to me. You point it down the runway, push the engines up, and the little inlets there, the more air goes in the inlets, the faster you go, and the more air, the faster you go, and before you know it, you're doing 300 knots. And fortunately, the guy up front lets us fly it. But that's the reason that they let us fly, is because they want to have us understand how much of fun it is and how much of the joy it is to fly with them, and to have that kind of a trust. You know, I can't land that T-38. I'm not supposed to land it, only in an emergency, but it's really difficult to land from the back. So I probably put my life in the hands of the astronaut, and the astronaut puts his certification and his life and his health and his ability to continue to fly in my hands too. It's a team. So that's what we're doing when doing simulations. That's what we're doing when we're doing real world cases. How often do you brief your surgical cases, or how often do you brief? I know you brief the simulations, and that's just like what we do when we go flying. And basically, if you see anything that looks unusual, you see anything that's a problem, everybody says stop. We'll handle it, and we'll figure out what we're going to do, and we'll immediately work that issue. It's very important, as I said, to pay attention to people that are working in support structures. These are the guys that maintain those T-38s that are older than I am, and if I have to trust them to maintain those jets as well. This is the office that aviator flies in. And the reason we get to fly as well is because things that might not give us a problem here when we're walking around here in San Diego, but if you're in flight or if you're trying to maintain level flight or you're trying to talk with air traffic control and do navigation, some of the medications you might commonly give to a person may interfere with that. So I have to know what the environment's like. And it's just amazing the aerobatics this thing will do, but the guys that are fly very much by the rules. So as I mentioned, trust, understand the environment, professional respect between people, professional respect as a team, figuring out what you're going to do in an emergency, having personal leadership when it comes to how you're going to handle things when they happen. We have to memorize things called the bold print, or what you need to respond very, very quickly. And you need to learn from the other person's point of view. You know, a lot of these patient simulators, I wonder how many people have actually been the patient and understood what it is to be the patient. Please do, you know, I think it's very, very powerful. Another place that we get to fly is in the Vomit Comet, so to speak. This is a KC-135, and now they use a DC-9. The first time I went out and did this, I felt like I was going to the guillotine because I'd heard the reputation of this. And basically what you do is you go out in a large aircraft. The pilot gets up to about 25,000 feet. They push the engines up. That pushes the nose up as well. They pull back on the yoke, and you get about 1.5 Gs as you're going up. They pull the engines back, they push the yoke over, and everything starts to float. It's almost like somebody opened up a can of levitation and sprayed it around the room, and everything starts to float up. And the first time I did it, as I mentioned, I was worried about how I was going to do, because this is my job. I'm going to have to keep my cookies together. And but I did fine, and I remember laughing, and I was actually singing as I was taken from some of my first parabolas, because it was just such a blast, and it looked like you were on orbit. You get about 30 seconds of floating, and then they say feet down coming out, and they push the engines back up, and they pull the yoke back, and you get 1.5 Gs. And that's when usually people feel ill, because they're sitting there talking about things. They say, how are you feeling? They turn their head quickly to the side, and then their gyros start to spin, and that's where they feel kind of different. So this is me in the back of the KC-135 doing my Superman push here. And actually I'm taking care of, there's a young lady who's working on her science experiment. She wasn't feeling so well, so one of the things you try to do is help them feel better. We can give some medications. She got sick and then immediately went back to her science. So, it can be quite provocative when you're trying to take care of somebody else who's having issues, when you're trying to keep your own cookies together too. So it's a lot of interesting. Here's another place we get to simulate and understand what the astronauts are going through. This is a shuttle training aircraft. It's a Gulfstream II, and they use this to do the shuttle approaches, about 1,000 before they land the shuttle. And what they do in this aircraft is they put the flaps down, the gear down, they put the engines in reverse, and they head towards the ground. And they have, from what they told me, it's like the aerodynamics of taking a Coke machine and throwing it off a bridge, and basically head towards the ground. And they're usually the astronaut on one side, the pilot sitting on the other side. There's an engineer, and the flight surgeon kind of stands in the back, and you watch the altimeter just sort of go down, down, down. And then the only time I'm telling myself, they've done it before, they've done it 1,000 times before, they know exactly what they're doing. But to me, it's amazing because you understand what is going on with the middle ear, and you understand that they only have one shot to land the shuttle when they're doing this, and so you can get a feeling for what sort of issues you might have to treat differently when you're taking care of that pilot. Let me skip over a couple of these things because of time. So we did support the shuttle. As a flight surgeon, it's an amazing time to be able to take care of your crews. We actually fly down with the crew members who were in front of the shuttle there, and three docs that are taking care of the crew members there. We get to crawl around in the back of the payload bay, and it's important. And besides just a gee whiz kind of thing, there's a guy standing looking at one of the in the back of the payload bay of the shuttle, looking at one of the radar thing. There's a very, very small group of people that are taking care of the crew. Those are two on either side. There are 2 flight nurses, and then 3 flight surgeons in the center that are taking care of the crew members. When you're with the crew member, they're doing their pressurization checks. It's an amazing feeling because you know you're one of the last people they're going to see before they go for their flight. And they're excited, they're ready to go. You can see these million-dollar smiles as they walk out to the spacecraft. These guys have been waiting 10, 20 years to be able to do what they're doing. Don Pettit's the guy on the right-hand side. He's on orbit right now. When they launch, it is an amazing event. If you have seen a launch, you know how much it makes you feel very, very proud to be an American. And the sound is incredible. It's like a storm coming at you, about 50,000 miles an hour. When it launches, there's a trail of material behind it. That's actually, you can see on the right-hand side, the shadow from the sun. And they hit 17,500 miles an hour 8 minutes later. And there's that same million-dollar smile on Eric Boe as he's launched into space, and there. Sandy Magnus is another one of my great lady astronauts, and she was getting ready to go for a long-duration space flight. So what happens to the crew members when they get on board? They immediately, or get on orbit, the fluid starts to shift immediately. It's whatever's in their legs actually equilibrates through their body, and so they get a really puffy face. The middle ear no longer has any gravity to associate itself with, and so the middle ear starts doing strange things. After some time, the blood plasma actually contracts. The weight-bearing bones no longer have any impact to them, and so they lose 1% of bone per month unless they do exercise on orbit. So pretty significant when it comes to the effects on the human body. I went over these things. The other things that are very important to pay attention to is the psychosocial and behavior health of the astronauts. You're trying to have them maintain a great performance at high levels. So after that glory of seeing the astronauts launch in the shuttle, we come back to the flight control room, and where we've done all those simulation times, we're going to be working with all those other engineers, and we've prepared. That's when we work the mission. There, as I mentioned, it's multidisciplinary, so we've got biomedical engineers that are working behind the scenes. It's almost like phone a friend. You know, the flight director talks to you, you've got a little earpiece in, and the flight director asks you, what should we do with this toxic piece of equipment? And the biomedical engineer says, stow it in the wet trash. And then I say, stow it in the wet trash. And so it's really nice to be able to have a group of people that are supporting you when they're doing this. As I mentioned, we're working with multiple engineers, and most of them don't have any idea of how the human body works, or have less of an idea of how the human body works, and I don't know how some of their systems work as well, so we have to get a common ground where we talk with them. There's several things that have happened on orbit. Now, some things I can talk about, some things I can't. These are some of the things that are very, very, very well published, so you don't hear about these things. Being a flight surgeon and being a physician and a nurse practitioner is like being a duck on a pond. You're smooth on the surface and you're paddling like crazy below, and this is what's actually happening in behind the scenes and things that we've seen in orbit. And I can answer questions after this if we have some time. We also are looking at circadian shifts. This is a schedule actually of when sleep shifts are supposed to occur. Actually, the gray areas are when the crews are supposed to be sleeping, and then you can see that all of a sudden they have to shift their sleep in the middle portion of their mission and then continuously move east. And that can impact the patients and the crew members' performance. After they land back at Edwards or at Kennedy Space Center, then we take care of them. They come off of the space shuttle, and they're, again, 2 or 3 liters of fluid down, so they're a little lightheaded. Their middle ears having issues, and so we have to be able to be prepared to treat that, as well as the shuttle and spacecraft have lots of toxicologic issues with if they have any sort of release of some of those hypergolic fuels, we have to be able to respond to that. So also in simulations, you have to be able to apply what you learn in some completely different situation. That last crew that you saw there that was landing was the Hubble Space Telescope crew. And then when they launched, they were not going to the International Space Station. They were going to the Hubble. And if they had an issue on orbit, they would not be able to actually dock with the International Space Station. They don't have the amount of fuel it was required. So we actually had to come up with a way that we would have another shuttle launch, and they would come close to the other shuttle, and we would actually take them from one shuttle to the other. Kind of a crazy way to do it, but we had to do it. And so how would we support the astronauts on orbit? Because it would be a good 30 days before we could get up to them. Well, we had to figure out how to take care of them from a nutritional standpoint and hygiene standpoint, and how are you going to take care of them from a psychosocial standpoint. And we fortunately never had to use that. But what we did use it for, which, as I mentioned, you got to be ready for new situations, is the Chilean mine disaster. It was a group of 4 flight surgeons that went down to Chile for that, and we used, it wasn't me, it was J.D. Polk and some other folks that went down there, and they used the same method of taking care of a person on orbit as we did down with the Chilean miners who were stuck below the surface there. So be ready to use the information you learn in the simulation in a completely different location. Well, and now the shuttle program has gone away, and now we're getting to and from the International Space Station via the Russians. Via Russian Soyuz. So we actually have flight surgeons that are supporting crews over in Russia, both for hazardous training and also winter survival training. The Russians have a long tradition, as we saw way back from the 50s. They launched the first human into space. And they use the same spacecraft pretty much that they used back in the 50s. It's tried and true. They've upgraded the avionics, but it's still a very, very tight location in there that they put 3 people into. They do lots of simulations like we do as well. Here's the astronaut Mike Barrett, who's another flight surgeon who got accepted to the Corps. He's working a simulation on how to dock with the International Space Station. They have neutral buoyancy labs like we do in Houston. They have over there as well. They do things in a very, very tried and true manner. Here's Katie Coleman. Coleman getting measured for her gloves by a guy who's the only guy that does that, and he's put it on the paper, and then they're going to sew up her gloves using that. They will actually to make a seat liner, they will put a person into the seat. This is a seat that's going to carry them into space, and when they land, they actually use plaster of Paris and put a mold in there, and then put the astronaut in to get an impression of her. And there's a guy who looks like Michelangelo who will start to scrape and make sure that there's no pressure points. And, the same guy that's been doing it for 50 years. And then Katie Coleman gives a thumbs up. She's ready to go. And that's important, and later I'll show you why. So when we launch over in Russia and Kazakhstan, as we mentioned, it's a former Russian or Soviet country. It is in the middle of nowhere. It's as large as Western Europe. And there's a reason we launched down there. This is a horizon picture, so we're starting to the left, and we're going to rotate around to the right. It's my friend Jose Flores, and we rotate on Kazakhstan, so there is absolutely nothing there out in the middle of nowhere. There's a few camels out there, which will blow your mind when you see that as a launch site. And they build their rockets out in Moscow. They truck them all the way down to Kazakhstan, and beautiful intercontinental ballistic missile that you're going to put 3 people on top of. They get ready in any weather. They're ready to go. But it's really nice to see former foes working together. Here's a Navy astronaut on the left-hand side, Mike Baker, and then a Russian general. You can tell because of the very large hat there he's got on. And it's very nice. They paint our flag on the side of this thing. They know it's an international event. They raise up the rocket the same way they've done it in the past. This is the same launch site that Yuri Gagarin launched from back in the 50s. They do everything the same way. It's worked. And very little unusual from our situation in that the shuttle was, loaded and people were away. These are all the press that's sitting below getting ready to launch those 3 crew members in a fully loaded rocket. It's crazy. The other thing they do we don't do is they have a nice blessing of the Eastern Orthodox priest to make sure everything is covered. So I think that's good. As a flight surgeon, we sit out in the search air rescue with an Mi-8 helicopter. That's something else, to be able to ride in a Soviet-era helicopter. When they launch, similar sort of thing, but we're closer, about 1.5 kilometers away, and the sound is incredible as those Russian intercontinental ballistic engines kick in. Same thing, 0 to 17,500 miles an hour within about 8 minutes. Space remains to be a very dangerous place, and so we have to simulate how we're going to respond to issues. They've had issues when their launches. There's on the upper right-hand side is the Challenger, and the lower-hand side is the Columbia. Left is the Apollo, and we need to be able to be prepared. And how do we do that? Well, we prepare via simulation. We prepare via practicing. We involve the DoD, we involve military to be able to respond to those things. We can't take up a huge amount of medication nor systems onto orbit because of the amount of space, et cetera, but we need to take medications up. And so how do you pick which medications? Well, you simulate, you figure out what sort of medical events have happened in the past, and then you can kind of predict what you need to have in the future. Then you need to train the astronauts on those and the crew medical officers on that. When we don't send, unfortunately, we don't send a flight surgeon or a physician up with each mission. They should, but they don't send them up. They usually will send up a crew medical officer, and this is a F-16 pilot that we've given about 20 hours of medical school to, so very, very rapidly. They're amazing. They will do exactly what you tell them to do in the same way that you've told them to do that. And I think it's the ultimate in telemedicine because they really are our hands and eyes when they're working on orbit. But a very limited amount of stuff that we can take up. We no longer have a defibrillator. Actually, we woke up and decided we need to put an AED on, which makes a lot more sense. We trained the crew medical officers on how to draw blood, how to do CPR, how to respond to medical emergencies. And here's our high fidelity simulator on board. Actually, you see 2 crew members that are doing CPR on a crew restraint device. And how do you do CPR on orbit? Well, you can either strap yourself with your knees, with the strap over your knees, or you can put your feet on the ceiling and push down. So that's what they chose to do. It's also very important this crew medical restraint device is isolated from the rest of the avionics of the station. Because if you were to shock the patient when you're doing a defibrillation, you could also shock the avionics and knock out all your control systems and things. So very important that we actually have arguments where we're going to put this thing because sometimes it overlays to some fire ports and things of that nature. And also the crew medical officers are very, very interested in knowing how to do this because the guy that they may be working on is their Soyuz commander who's their ride home. So they actually will pay attention on how to do CPR quite well. So, you know, we also will maintain the environment of the space station. We have to be able to respond to toxicological or other exposures. Countermeasures are very, very important. As I mentioned, 1% of bone loss per month is a lot, and you don't want to come back and fracture themselves. So we spend a lot of time doing exercise on board. The human patient simulator, you can see Haldor in the upper right-hand corner here, is very, very important because we can take the human patient simulator, put the same physiology into it that we have on orbit and also post-flight, and then respond to emergency, so to speak. And why do we do that? Well, it's to be able to communicate, to be able to run through the procedures and validate them, to be able to use a physician in the loop. It takes extra training to know how to talk on the loops. And so Hal's group in the MOST project, we did a lot of work with that, and also on the KC-135, as we mentioned. We do part test training first. We sit around and do case reports. Then we actually sit in mission control. That's the second little picture there. We talk with the other flight controllers. We use human patient simulators to run through our procedures and such. We do generic simulations in Mission Control Center. I'm a family practice guy, so I've been taught by anesthesiologists, you know, 90% of the time is just boredom, 10% of the time sheer terror. And that's what happens when it comes to mission control. Most of the time you're working, you know, with generic simulations and going through the different situations, and then usually they'll pull out what's called a green card and drop some sort of medical issue on board. But we have to be able to respond to fire, toxic spills, depressurization, radiation events. And it's uncanny when you do that. We had a radiation simulation, and the next week we actually had the actual launch. And right when that happened, we had the sun decided to burp out what's called a coronal mass ejection, which threw this big amount of material. Well, the same lady who called me during the simulation, the radiation support specialist, called me and said we had the same thing that we had during the simulation, and we responded to it in the same way. So it's amazing, I think, how powerful it is to be able to simulate things and get ready for that. You can't simulate everything. This is some of the countermeasures material. This is a treadmill on board that broke and broke in an unusual way that you wouldn't have expected to, because we hadn't been able to test it as much in zero gravity. So we had to come up with a fix for it. Same sort of thing. Here's another thing that we weren't really expecting. This is the harness that actually holds the astronaut down in there when they're doing their countermeasures, and it wasn't labeled correctly. This side up, well, there's no up in orbit, and so what they should have said, this said to your head, or drawn a little picture of a person, because they mounted it upside down, and when they did that, all the straps came loose, and so they got some good sewing material out and repaired it. But those are the things you don't think about until you're in the environment. The other thing you can't tell is this is actually the shuttle coming in the International Space Station, and you can see those little lights that are on the shuttle. You might be able to see it. That's a radar, and the radar actually, that's the visible portion of the radar, but there's also a infrared, or the invisible portion of the radar that you would not be able to see. And if you had a camera out with a long-distance camera trying to take a picture of that shuttle coming up, you could potentially injure your eye. So those sorts of things you cannot simulate on the ground until you see it. We saw this we were looking through all our pictures and saw this picture and goes, wait a minute, what's coming out of that radar? Wait a minute, how'd they take the picture? Wait a minute, what's the lens they're using? Oh, we need to make sure that the crew doesn't take that kind of a picture again, because they could potentially injure their retina. Here's that $1 million smile again. Mike Fink, he's going out in a Russian Orlan suit. We have to be able to talk with the Russians on how their systems work. This is actually another picture of the space station and the descent module of the spacecraft. This picture was sent down a couple of weeks ago by Dan Burbank. The pictures that your patients will send to you are just simply amazing. That's the Comet Lovejoy that was supposed to dive into the sun but didn't, and then gave some really incredible views from the Earth. The other thing is the sun has been very, very active recently, and the auroras have been amazing. So the pictures they send down are really just incredible. So after they launch on a Russian spacecraft, they're on orbit for 6 months. We'll bring them back down to space. This is the Soyuz. On the left-hand side is the orbital compartment. The middle compartment is the one that they actually return in. The right-hand side is the so-called service material there, or service compartment. They will like to land normally. They'll get about 1.5 to 3 Gs. This is a picture of actually coming in the entry there. You can see when they're in orbit and they enter. And they like to do a nice slow descent and then land by parachute. But the spacecraft is really smart. If it has an issue with itself, it will decide, I'm coming down now. I've got either depressurization or my avionics are wrong, and it will actually bring the astronauts down very, very quickly, and they can go through anywhere from 8 to 10 Gs coming down. So we need to be able to protect for that. Here's a map actually of in Kazakhstan where we go and get them. We'll send out a flight surgeon to the prime landing area. We'll also send them out to the ballistic landing area, again, in those helicopters. And when they come in like the old style. They come in, but they're not going to hit the the water, they're going to hit the land, actually. So here the Soyuz spacecraft coming down via parachute. About 5 meters above the surface, there's a radio altimeter that decides I'm now above the surface, and it fires. And so the smoke you see there is not the crash itself. It's actually some retro rockets, so to speak, that are firing. But the astronauts say that when they are coming back from 0G into this and they hit the ground, it's like a controlled crash. It's like they feel like they're in a car accident. Here's when they're landing in a plowed field. When the spacecraft lands, 80% it's on its side. In this particular case, it landed upright. There wasn't a whole lot of wind. And the 3 crew members are inside that descent module. You can see a lot of the burned away heat shield. And when this is a picture of them right after they landed. They actually are still inside. They're landed on their side there, and you can see how compressed things are. And you can see how much stuff they brought back with them, materials and payloads and things of that nature. And so you can see what kind of problems you might have and what you need to be prepared for when it comes to flail injuries and impact injuries. When they bring them out of the top of the Soyuz spacecraft, they bring them down, and this thing looks like a big bread kind of a tray, and carry them over to see the press, and then we bring them back to Moscow and back to the United States via those helicopters. I have a little more time left, and I'll talk very briefly about an analog. You know, you can't take everybody to space, and you can't take everything to space because it's very expensive. And so what NASA does is we need to use analog environments. And one of the analog environments is this Aquarius habitat, which is basically a very small chamber that's down off of the coast of Key Largo. And they'll take down 2 habitat technicians, and in this case, a crew of 2 astronauts and a real surgeon and a flight surgeon. And it's basically the same as space flight without the zero gravity. We have a mission control center. We do space medicine training there. The upper left-hand corner, this is a map of where the habitat is. It's over a reef there, and the habitat is in the upper left-hand corner, and the right side is all the different mapped areas where you can go. And they're mapped, and they also have lines there, because once you go down for more than 24 hours or a certain number of hours, you can't come up without going through a decompression cycle. Otherwise, you'll get what's called the bends or depressurization illness. And so those lines are out there to be able to reach you, get back to the habitat in case you have an issue. And so you need to go back to the habitat rather than servicing. We used to call it the surface is not an option. You need to go back to the habitat. When we arrived into this environment, it was like you were coming into another world, into an outpost, into the Aquarius habitat. 47 feet below the surface, and approaching the habitat there with high-pressure scuba tanks. It also tells you what kind of training you can get. I was basically a skin diver, you know, just snorkeling, and we got 25 dives in, then the next dive I had was a saturation dive. So it tells you when you simulate things and when you have good training what sort of things you can get into. We did things down in Nemo. We built things. We were actually the upper right-hand corner there trying to test a new spacesuit to understand the balance and how you could weight things so we're not falling down as much. Also, the right-hand lower corner there is Tim Broderick, a surgeon from Cincinnati, and he was working with a navigation device that he has in his hands and robotics as well, from remote-guided robotics. We did medical research there, the same research that we're doing on the space station. You can see Heidi Piper there, Definition Piper, with a reaction device actually checking how our reactions are based on some sleep shift issues. Jose down there, Hernandez, is checking some metabolic experimentation. On the right-hand side, I'm getting blood drawn, and we found that our immune systems were a little blunted, just like they occur on orbit when it comes to T cell function and white cell function. So it's a good way to be able to test things that you're going to test on orbit. You can test there as well first. We did remote surgery. There's a surgical setup there. It was connected all the way to the University of Washington. So we had, you know, a fair amount of challenges. Not only that, you know, you can't bring an entire robot down. You have to take it apart and put it in little pots and bring it down, and then you have to set it up and get the communications. The other challenge was that there were a lot of beautiful things outside. That upper right-hand corner there is all the fish, and it was really difficult to go to sleep. It was almost like watching a screensaver with all the fish at night, and I had to really just turn away and then not look at it. It was extremely relaxing. Being inside there. We ran ACLS drills like you guys are doing with simulations. We couldn't take some of the equipment down, so we had to actually refer to some equipment, but we ran through the same procedures. We did not have a mannequin there. We actually had to use another person, we didn't do full compressions. But we went through the procedures, of course, and we compared how a person would do in this location and how they would do on orbit. We did have problems. You know, we rushed a checklist. We did some hard hat diving. You can see us loading a hard hat there, and with an air supply. And we had issues with the checklist. We had handovers of the checklist without actually doing the correct handovers, and we had time pressures to get it done. And we had an issue where the air that was going to the hard hat wasn't sufficient. We immediately saw that and went back to our procedure. So the bottom line there is that procedure problems do happen whenever you're doing a simulation, whether it's real or if it's during an analog mission, and just pay attention to the checklist. Other things, like I said, were different from spaceflight, where there's live things outside. This is a very large grouper, and I had an out-of-body, or I had a different experience there. And most of the time at your house, you have an aquarium, you're looking inside, looking at the fish. But in this case, the fish were looking in at us, looking to see what was going on. Just very, very different. He was the boss grouper, really large guy. Had a very, very small support staff. It was very important to take care of your family members. We had Mother's Day there, and so we had messages from our mothers. I have a message from my Japanese mother-in-law that we sent up. And it was also very important, as my wife's sitting in the center there, this is a group that we brought our families in. We had a teleconference with them from the habitat, and I could not believe how powerful it was. I mean, for 12 days I was having a great time, but then to be able to interact with my family for about a half an hour was extremely powerful. So much that when, if anybody ever, we have the same sort of a conference with family members on orbit, and so now I know exactly how important it is for that crew member to be able to talk with their family members via telephone or via a conference. So coming out of the analog environment, it was a little bit like being born again. I mean, coming up after being 12 days under the ocean there, and coming out and smelling the earth and smelling and seeing things, seeing green and things was just an amazing experience. And you get a little bit of a glimpse of what it's like. Like I said, try to put yourself in the position of other people and understand what it is, what they're going through. I don't have much time left, but I just want to mention there's a couple other simulation locations. Desert Rats is one out in the far west out here, and we're trying to come up with a new mobile habitat where actually the astronauts can unhook from the habitat itself and do an EVA immediately. We want to be able to use this on the Moon and Mars, and with a remote guarded arm as well. And I know a lot of people have fantastic ideas. We're looking, it used to be NASA was the top of the spear when it comes to new innovation. You all are doing all the new innovation. And so we're bringing things commercial off the shelf. But the challenges we have from commercial off the shelf is that we're limited by power. We only have so much power on the space station. Mass is expensive. It's about $10,000 a pound or so. Volume is very important. We've got stowage. We're putting things everywhere on the space station because we don't have any space left with a lot of that. Time and also money. It's very expensive to send things in orbit. But the bottom line is that simulations are extremely powerful. Keeping your simulations realistic, and it's the critical element. We're using space analogs as well. Human space simulators like you guys have got downstairs. And then we put those and we bring them into mission control. We integrate them into mission control with the crews, the crew medical officers, and then later in extreme environments. And my bottom line when we're doing simulations is we test the people, we test the equipment, we test the procedures, and we test the communication, as I said, is the most powerful part of what we're doing. So again, thank you so much. It's been wonderful, and I can take some questions.